Welcome to the lesson summary video for the Math 1 task, Floating Down the River. This is a solidify understanding task, and as you can see at the top, the purpose of this task is to solidify student understanding of a function, so that's the first goal, and the following key features: domain and range, increasing and decreasing, x and y intercepts, rates of change, maximum, minimum, and discrete/continuous. So we have these kind of vocabulary terms that come together in related pairs. Everything has a pair, x-intercepts with y-intercepts, except for rates of change. So in some of the cases, we need to provide both. In some cases, we're making a decision, whether, like the last one, whether it's discrete or continuous. So let's keep that in mind. First off, so for the first goal being solidifying our understanding of a function, let's just remind ourselves that for something to be a function, every x has to go to one y. So we have the scenario where Alonzo, Maria, and Sierra were floating down the river in inner tubes. Alonzo decided to collect data comparing time with depth, and Maria decided to collect data comparing distance and time and distance. So we're going to look at Alonzo's data. So it says, use the data collected by Alonzo to interpret the key features of this relationship. So without even graphing it from the table, I can figure out some of the key features. First of all, is it a function? Does every time go to one depth? And as we look at the table, we can see that's yes. Time 0 goes to 4, 10 goes to 6, 20 goes to 8, and so on. Every time goes to one depth. So it is a function. So we can analyze the domain, range, etc. So let's start with domain. Domain of a function is the set of x values that the function covers. So his lowest time was starting at 0. So 0 is less than or equal to x, which is less than or equal to his highest time, which was 120. And that's inequality notation. So we could write it in interval notation as 0 to 120. And remember, this square bracket means that the values of 0 and 120 are included. So now I could also think about the range. So the y values, let's look and see what's the lowest value of depth. Right here we have 4, so we can go ahead and label that as a minimum. And the highest value of depth is 12. That's a maximum. So as far as we know from the data that's collected, our range is going from 4 is less than or equal to y, which is less than or equal to 12. So we could write that in interval notation, 4 to 12. And when we're talking about a domain interval, it's understood that it's based on x, and a range interval is understood that it's based on y. So let's think about some of the other things we can see from the table. So first off, we can think about increasing and decreasing. So as we start off here, I can see 4, 6, 8, 10. That's increasing. And then it goes 6, 5, 4. That's decreasing. And then it goes 5, 7, 12. That's increasing again. And then it goes 12 down to 5. And so that's decreasing again. So we can see it's alternating between increasing and decreasing, increasing and decreasing. So let's kind of look at a graph now to consider that. So as we can see, it starts off with an interval of increasing. And I'm drawing this in to show that that's the case. I don't necessarily know that the shape is going to be a straight line. I'm just making some assumptions there. It may not be. It might have looked more like this. But either way, based on the data that we have, we can pretty confidently say that as increasing most likely. Then we can see that it's decreasing. Maybe it's decreasing more at a slope like that. And then it's increasing again. And then it's decreasing. Again, I don't exactly know what it looks like in between those points because he didn't collect that data for us. But I'm assuming that that's something like what it might have been. And it may have been more straight. It may have been more curved. I'm not sure. But we do know it hits those data points. Consequently, we don't know for sure that 4 was the minimum depth and 12 was the maximum depth. It's possible that at some place in between it went higher or lower in between the data points that we have. But based on the information we're given, it's fair to say that that's the min and the max from what we know. But what's important is that this, even though we only have a set of 12 data points, we know that this is a continuous scenario because at every time there's going to be a certain depth, whether it's 0 seconds, 0.1 seconds, 10.99953 seconds, every time had a depth because he was always on the water. There wasn't a time where he just teleported over to some other location. So this is a continuous situation. And when I say continuous here, I'm specifically referring about the function that would represent this scenario for all the times and all the depths. The data table that we're given is a discrete data table because it only provides us snapshots every 10 minutes. So I just want to clarify that. It's a discrete data table, but it's a continuous function that we're considering when we would look at the graph. So let's talk about increasing and decreasing now. So as we said, we have these intervals of increase right here that we can see from the table as well as on the graph. And so this first interval of increase, I'm going to now use interval notation. We always base increasing and decreasing off the x values. So the first interval of increasing started at an x value of 0 and ended here at an x value of 30. And I've elected to use a square bracket at 0 because it looks like it starts off increasing. At the top here, at the peak, we don't know. Well, we do know it's neither increasing or decreasing because it's changing direction. So at those places, we use a normal parenthesis to indicate that it's neither increasing or decreasing. Then we can use this little symbol here means or, so increasing is in this one interval that we just did here, or this other interval that we're going to do here from an x value of 60 up to an x value of 90. So we could also have 60 to 90. Then the decreasing, we saw those two sections. So similarly, we're going to write two intervals for decreasing. And that's going to be from 30 to 60. So notice that's the place in between the two increasing intervals where they ended and where the other one started. And then from 90 to 120. And we can assume that it's continuing to decrease at 120 if he had continued to collect data. So that takes care of increasing and decreasing. Our maximum depth was 12 feet. And we can see that on the graph right here. So officially that's called a global max. And our minimum depth from the data provided was 4 feet. And so that occurred twice. So we have a global minimum here and a global minimum here. And the reason I use this term global is to distinguish from these other points, such as this point right here, where we have a peak for that section, but it's not a peak overall because the global max is higher. So we call those a relative max. It's a maximum relative to the points around it, but not for the whole graph. And we'll talk more about that, especially as you get into higher level math classes, but I just want to introduce that terminology here of global and relative. So when we say max and min in this course, we're typically referring to global max and global min. So last things we want to consider are intercepts and rates of change. So without even looking at the graph, I can tell from the table that my y-intercept is there at 4, and then I can confirm that on the graph. There's our y-intercept, and the x-intercepts would have to be places where the y value is 0. Since the depth is never 0 in the table, we can assume that there are no x-intercepts for this graph. So there's one y-intercept at 0, 4, but there's no x-intercepts. So now we can consider the slope, or the rates of change, I should say. And we can consider the rates of change for each 10-minute interval. So in the first 10-minute interval from 4 to 6, at a rate of change of 2 feet over those 10 minutes, and then 2 feet from 10 to 20 minutes, and 2 feet from 20 to 30 minutes. And so you can see that straight lines, the same slope straight line, approximates the rate of change for each of those gaps. Then we had a decrease of 4 over this interval, then a decrease of 1. You can see how that's a less intense slope. Another decrease of 1, then an increase of 1, so same slope but going up, then an increase of 2, so a steeper slope, then an increase of 5, which is the biggest rate of change there. So you can see that's the steepest line I'm going to draw, and then decreases of 3, 2.5, and 1.5. So getting smaller every time in the amount of decrease on the secant line that I'm drawing. And so those are the rates of change over every interval. So one way we might phrase that biggest rate of change is that it was 5 feet in 10 minutes. Or we could even say half a foot every minute. So I trust that you'll be able to take what we've done here on this first problem and apply it to the second problem to find all of those attributes for Maria's graph that she's already plotted for you, comparing the distance to the time. And then you'll be able to answer problem 3 with the agree and disagree statements that Sierra has come up with. If you need help with the Ready, Set, Go problems aligned with this task, please check out the Ready, Set, Go student support videos in Canvas.